In this video, I'm going to talk about derivatives in the context of free-falling objects, kind of near the surface of the planet. So if you have an object, let's say that's being dropped from a helicopter, let's say 1,000 meters above the ground. So you're 1,000 meters above the ground. The object is being dropped. We kind of want to find out the position of the object after it's been dropped, and then we want to find out the velocity of the object at different times after the object is dropped. So in physics, this is a very classical example of Newtonian mechanics. Position of the object S of t is after t seconds is given by 1/2 g t square. Okay, where g is the gravitational constant, and that value is g is equal to 9.8 meters per second square. All right, we don't need to worry about the unit so much. So we are going to plug in g here to get the position of the object. So S of t as a function of time is going to be 1/2 times 9.8 times t square, which is going to give me 4.9 t square. Now we are going to use this formula to find the position of the object at any time. So if you want to find the position of the object after 5 seconds or 3 seconds or 2 seconds, you can just plug in the corresponding value. So let's say we want to find the position of the object after 2 seconds. So we are going to set t is equal to 2. So S of 2 is going to be 4.9 times 2 square, which is 4, and whatever number it evaluates to. Now we want to find the velocity of the object at different times. So velocity, by the way, is defined as the change in position with respect to time. Once again, velocity is defined as change in position with respect to time, which right away tells me the following. The velocity of the object as a function of time is going to be the change in the position of the object as a function of time, which is to say that it is going to be the derivative of s with respect to t, ds over dt. And now this derivative is something we know how to find, either using the definition, which I will use here, or just using the formula. So what is the derivative of s? So my v of t is going to be limit h approaches 0. In this case is going to be s of t plus h minus s of t, all of it divided by h. So this is exactly the definition of derivative, which also this ratio, by the way, this ratio right here, it kind of gives you the change in the position of this object, instantaneous change or instantaneous velocity. Okay, now let's kind of play around with these numbers. What do we got here? Limit h approaches 0. So 4.9 times t plus h whole square minus 4.9 t square, all of it divided by h. If I were to simplify this, this is kind of what I get. So this is the definition, and then I square it, which gives me this, and then I subtract t square, and I factor out this 4.9. So if I go further, I can factor out an h, that's going to give me this. Now this h and this h in the denominator are going to cancel. That's going to leave me with 4.9 times 2t plus h. Now, as h approaches 0, this term is going to vanish. That's going to leave me with this, and that gives me the velocity, which is 9.8 times t. Now, my velocity formula, v of t is equal to 9.8 t. Velocity technically is a vector. It has a magnitude and a direction, but we don't get into the details of that. Here we can just think of it as a number. What is the velocity? Velocity without the direction is called speed. And sometimes we kind of mix both of these terms informally. Now, having said that, this is the formula for velocity. So now I can go ahead and find the velocity at whatever point at whatever time I want. If t is equal to 3 seconds, I just need to find the velocity of this at t is equal to 3, which is gonna be 9.8 times 3, which is, by the way, gonna be 29.4. So given the position of a falling object, we can go ahead and find position at, given the formula for the position of a falling object, we can find the position at different times as well as the velocity. And another very typical or classical problem that people ask, what is the velocity of the object when it hits the ground? So when it hits the ground, the distance is actually 1,000 meters. Because in my example, I said that the object is being dropped from 1,000 meters above the ground. Now, that tells me that S of t, that the position of the object is 1,000 when it touches the ground. So remember, S of t is equal to 1/2 gt square. Now, or I could use this version, S of t is equal to 4.9 t square. So 1,000 S of t is equal to 4.9 t square. So t square is going to be 1,000 divided by 4.9, and t must be equal to about 14.29. Approximately 14.29. So after the ball is dropped, roughly about 14.29 seconds later, okay, it will hit the ground, and at that time velocity is gonna be v of t is gonna be 9.8 times t. So v of t is equal to 14.29, which is gonna give me 9.8 times 14.29, which is roughly about 140 meters per second. So this is an application of derivative in the context of real world problems. So this is a very simple and very useful example that's coming from physics, but derivatives have application in all over many different fields. So it's important for you to understand how to apply the concept of derivative into different real world problems, how to apply the concept of derivatives to solve actual meaningful real world problems. I hope that this discussion was helpful. Thank you very much.